So let's just quickly check how the Fourier transform could help us. So let's draw this again. So let's assume we have a signal. And this signal is x0. And this signal goes from 0 to n minus 1. So it has length n. And there will be some non-zero whatever values in there, whatever that thing is. And then let's assume I have my filter here. And so this is f of n. And let's just assume right now it only extends to the positive part. So let's assume it has here some things. But this is 0, 1, 2, and so on. But starting at k, this thing is 0. So we're doing f of n is 0 for n bigger equal than k. So it has only k non-zero components in here, right? So we have to be a little bit careful. I should still change in the notes. Once in a while I use k to be, for the absolute value here. So meaning it goes for the positive and negative part, and now I just assume that this is 0 here for a negative part, and then only has here the width k, right? So I think I have a slight, in the notes I think I use both, and this is not consistent. Good, so now we do the convolution, right? Okay, so we should do the convolution here. And at the end we'll get out our n, our signal x1 of n, which is just the convolution of the two. So now it's convenient to convert this in the slight way. So again, remember what we should do. What we should do with this is the following. We should take this filter, okay, flip it over like this. So we just flip it over, and then simply, put it, shift it to every single position, right, and then compute the inner product with that, and that's going to be the output at the time, right? And so that is in principle not a problem when I'm anywhere in here. The only problem is at the boundary, right? So we'll get some problems that when we are operating in a boundary because we're missing some values. So as we said, there are two ways to do it. One is to do some zero padding. So if we're adding some zeros, so for example, in this case, if we add it here on this position k minus 1 zeros here, so to each of them, so if I added k minus 1 zeros, then you can see I take this thing, I flip it over. So the first one will be when this one will be this one will be here, and this one will be here, right? So I have k minus 1 position outside. Okay, so I'm thinking of this should simply be 0 here, right? So that's fine. And then I go over it, and this goes well all the way here. Okay, I don't have to worry about the other side. If I just simply assume again everything is 0 here, I'm doing fine. So in principle, so now if I looked now at a vector tilde, which was the same vector but had k minus 1 zeros padded, right? I would get this is one way to actually compute it, and then I wouldn't have to worry about boundary conditions in here, right? So now if I do this, I can do also a convolution here between these vectors. So what I'm saying is the following. If I take x tilde, so if I take x tilde and 0, so if I take the following, I take the following convolution over k of x tilde 0 of k times f of n minus k tilde modulo. So let me just call the length L is n plus k minus 1. And so if I do this over all k, so this goes from k is 0 to L minus 1. And now I'm going x tilde 1 of n. So this is now a convolution where I do the following thing. I do the convolution just like beforehand. But what I do is the following. I compute all the indices modulo L. Right? So as soon as I go beyond, so L, so the L is something here. I can imagine something here. So there's something the L. So this is the n minus 1. And this will be the last one. L is n plus k minus 1 here. Then the statement is the following. If I do this, what's called, this is the cyclic convolution. Whether I think that these two signals are expanded over the whole real line with everything else that's not there as being 0, and I do the convolution in the standard way, okay? Or whether I now do the cyclic convolution, which only extends over this length L here, as long as I pad, and so instead of, since it's cyclic, these positions here, modulo L, are the same as these positions here, so I can also think that I'm adding actually the zeros up here. Is that clear? So I can just take this one here of length L, where I simply add a few zeros here, add a few zeros here, and then doing the convolution in the cyclic manner that's written down here is exactly the same as taking the convolution of the original signals, where I assume that the signals are infinitely long, and everything else that's not there is 0. Is that clear? So I've just reduced basically a problem where this could extend for, to infinity, and I'm just now having something that has fixed finite length and where everything is cyclic. Okay, so, and now what is then the output here? What is the output here? Well, if I look at again, the first from position thing to n minus 1, okay, then within here, this gives me exactly the same as if I had computed the output over these infinitely long sequences. Is that clear? And so why is that useful? Because this thing here, we can compute efficiently. So this thing here, we can compute in a complexity of something C log n times n. Okay, so it's not quite linear. But we can compute this efficiently, and so this is completely independently even of what this particular. So sorry, I should write here L. Okay. So in C log L times L, and so this doesn't crucially depend on what the k here is, right? Because even if the k is equal to the n, then all that happens is that this L is twice 2 times n, essentially. And so you just get a factor of 2 in here, right? But it's not quadratic, right? It's only just you get a linear factor 2 in here, and then you get the log in here. But the log is very mild, right? It's almost a constant. Is that clear? So irrespective of what essentially this k here is, how large the k is, if you do this, if you pad it, if you look at a sequence that's a little bit longer, namely the length is n plus k, then you can use the Fourier transform to compute this cyclic convolution here, which gives you exactly what you need. And the complexity is just a little bit more than linear in L. Okay, so it's something like 2 times n and times the log here, right? Times some small constant here. And so how do you do it? You do it with respect to the fast Fourier transform, or with, in the Fourier transform, which then itself can be computed efficiently. So if I take, in general, signal x n, where x goes from, for n is from 0 to L minus 1, so I take a signal of length L, then the Fourier transform, x hat of, let's say, k, is simply of the form over all n, x of n by e to the minus 2 pi j over L times n and k. And you can go backwards by computing x of n. So it's simply a transform, a one-to-one transform. K is 0 to L minus 1 of 1 over L x hat of k times e to the 2 pi j over L n k. So this is a pair, okay? So this pair is a one-to-one transform. You can take a vector x, you compute it, you get a vector x hat of the same length, and you can go backwards. So it's a one-to-one transform. And the miracle is that this thing here converts convolution into products. So it means if I have a vector x and I have a vector y, and if we write the convolution as star, so this convolution is exactly this sum that I've written here, this cyclic convolution here, right? So then this is the following. You're taking x, you can convert it via the Fourier transform to x hat. You're taking y, you convert it via the Fourier transform to y hat. Okay, and then to get this convolution, this simply corresponds to the pointwise product. Right, which is very easy to compute. So in order to efficiently compute this, or in order to compute this convolution, what you can do is you transform both of them into the Fourier domain, you multiply them, and you take the inverse. So the complexity of the convolution is basically 3 times whatever the complexity is of doing this transform here. And it turns out that you can do this computed the transform. So there's an efficient way. So the fast Fourier transform is an efficient way of structuring this computation. So the old statement is this can be computed in a form that looks a little bit different than that. It's kind of a recursive algorithm how you can compute this. This is essentially exactly the same computation, right? You see that the only difference is that you have here a plus instead of a minus, and you're having here a different normalization, but that's not really a big deal, okay? And so the statement is that you can efficiently compute the Fourier transform. You take the signal, you take the filter, you take the Fourier transform, you multiply them, you take the inverse transform, and that's exactly the same as if you had done the convolution. Okay? Now, is this worth it? Really depends on whether or not this K has, or the filter has large support. Perhaps doesn't, right? Because the whole point of a convolution and that is that the support is not very large. So if it's not very large, it might not be worth like this. But if it is large, perhaps it is worth doing that. Okay? Good. So now let's go to a few other small points. So let's just quickly discuss still 3 points. 2 of them are actually kind of generic, don't really have to do with neural nets. They could also be useful for other cases. And the third one does depend on neural nets. And so the 3 topics are regularization, dropout, and data augmentation. So let's first start with data augmentation. That's very easy, and it has actually nothing to do a priori with neural nets. It's a very basic idea, but can be quite useful. Okay, so what is the basic idea? Well, data is expensive, and so if you want to train, how well you will train depends very crucially on how much data you have. So sometimes there are ways to create more data from the data you have, right? So for example, let's take one of the standard tasks, which is the NIST handwriting recognition task. So it's these days this is something fairly considered very simple, but probably 10, 15 years ago this was not so simple. And what it is simply a set of pictures. These are 8 by 8 pixels. And in there, they're simply handwritten digits in there. Okay, so all these are, you're having, you know, a few thousand examples of zeros, ones, two, threes, etc. Right? And so this is your data set. So, and you can train now your whatever neural net or whatever your classifier on this, and then you give it some, maybe a 5, and hopefully will classify it to a 5, right? So that's the task. Now, you know, compiling such data set is quite expensive. You have to take it, clean it up, maybe normalize it, with all this kind of stuff. So wouldn't it be nice if we could maybe, instead of having the few thousand examples which we have of a 5, generate a few more examples out of this, which are, you know, clearly also 5s, so there's no question. But for the computer, it's not so going to be clear that this is a 5, and so it can actually still train, right? So any ideas?
Maybe rotations?
Right, so clearly what we could do is, so maybe we don't just want to rotate it to, you know, like this, okay? Maybe you also want to, that it recognizes, or, you know, could also be interesting, recognizes in slightly off-hand positions, right? So you could do rotations. You can clearly also, for example, maybe shift, or you could maybe scale things a little bit, right? So all of these things are operations that we clearly know, you know, this should be invariant to these operations, right? Now there might be some limits, because perhaps you have only 8 digits, you know, you cannot, I mean, there's a limit to how much you can rotate, there's a limit how much you can shift it, etc. But you might be able to do this, right? There are other things you could do. For example, you could add a little bit some noise to it, right? So you take this image, you add some noise to it. Now, for you, this is a trivial operation as long as the noise is not too much. But for the computer, he simply sees, you know, a different vector, right? And depending on how much the noise is, the vector could be significantly different. And so it might become, if you train it now with respect to that, and it can still learn, first of all, have more data, but it might also become more robust, right? Any more slightly sophisticated things that we could do? Mixed? Mixing how, exactly?
For example, you bootstrap fragments of one picture and half of another one.
Yeah, so but the point is, you know, I want to have labeled data, right? So what is if you take a 5 and I mix it with a 3, then what is my label?
Just fragment of 5 on a 1 or 3.
But then what would be my label for that?
1, because it's the majority.
Okay, so that's like adding noise, and the noise is maybe more structured, okay? It's not clear why you want to confuse it maximally by giving it, you know, it's like someone writing, then erasing, then writing again, perhaps. Yeah, so perhaps if you want that, you could do it, okay? Okay, any other, we talked about at least one technique which we could use, which is, you know, maybe not so trivial. Did we talk about any other technique that one could use for things like images, perhaps?
We could change contrast.
Yeah, so we could change contrast, maybe, absolutely.
Do edge detection and give it the output.
Oh, sorry?
Do edge detection?
Yeah, so we could do some image processing things, yeah.
So adding like polynomial features or something.
Can you explain?
Okay.
Okay. Okay.
I don't know how it was like expressed in the course. So for each feature,
you're adding extra things, yeah. Yeah. So the input, yeah, you could probably, yeah, you could do this, yes, but that's going to be independent. That you can do. So we're talking about data augmentation. We're talking about getting more data points, and then of course for every data point you can do some feature extension or something. Yes.
And maybe PCA and generative.
PCA, right? So we learned exactly about PCA. So what we could do is we could run some PCA over this thing, and then only keeping the first two, you know, keeping the first so many components and so on, right? So this would be another way of adding noise, but it would be in a more structured way of adding the noise, because we know that that's the best, to some degree, the best representation if we're doing that, right? So the point is that, you know, some of you maybe take whatever, maybe you have the edge, maybe you have the whatever edge detection thing and so on, right? So there might be what, you know, the project you do. Perhaps you can look at the data and shift it and so on and get extra ones, right? The point is that if for you, shifting that by 1, you don't even realize that's something different, because you don't have any absolute reference of where you're looking at, right? But for the computer, if you shift it by 1, this is a completely different input, right? I mean, there's absolutely zero correlation to the thing, because shifting it by 1, you know, that, I mean, it's something that has for the computer doesn't know about symmetries a priori unless we would build in some symmetries into the detection itself, right? But if we just take something like this, where there's no symmetries built in, then it doesn't know about it. Clear? So in general, this technique has nothing to do with neural nets itself. If you have a problem, data is sparse, particularly labeled data is quite, can be quite expensive. Perhaps there's a way to take this labeled data, add noise, rotate it, any symmetries, anything you can think of, so to have much more labeled data that perhaps you can use for your task. Make sense? Okay, so that's number one. Number two, okay. What about regularization? Now, neural nets, by their very nature, have been observed to be much less prone to overfitting. So even if you take a neural net, and it has, it might have hundreds of thousands of parameters, and you give it maybe a simple function, it's much less likely to get, to completely crazy overfit as if you, for example, took a linear schemes. Okay, so linear schemes are much more prone to overfitting, but it doesn't mean that neural nets don't overfit at all. Okay, they can still overfit if you don't have sufficient data, and so you might still add some regularization term, and typically we had something like the W, and so this could be now all the W's in the neural net, right? Often we're having that, right? The sum of the squares of the weights. Now, often in neural nets, typically you don't penalize the bias terms, but you only penalize the weights themselves. Okay, so you would only put this regularization on the weights, not on the bias terms. And so so what is it now, right? So you're having some L of the weight, and then maybe you're adding still this times an eta here, right? And now you take the gradient with respect to this L with respect to W, right? Of the whole thing. So maybe this is L tilde, and so you take the gradient of L tilde. So you're going to get your usual gradient that we can compute with the back propagation algorithm, and so then you're going to still get you get this. So let me just write this, maybe the ith term here. So meaning I'm looking just at the ith weight and see how much this changes, right? So if having this, and then I still get here plus an eta of times the wi. Sorry, eta times wi, right? So this would be the derivative with respect to the wi weight that I have. It's just the usual derivative from the gradient vector here, if I'm looking at the ith component, plus then I get this term from here, right? So now what happens in the gradient step, right? So if I take in the gradient step, what happens is that if I'm looking at wi, and I'm looking, let's say, at time t plus 1, so I'm looking after I take the next step, then this is what? This is the wi at times t, and then I go minus a little bit in the direction of the gradient, right? So I go minus whatever kappa times the delta L tilde W of I, right? So, and so what would this be? So if we do this, well, then this will be, it's the Wi at times t, and then I have minus the kappa of the gradient with respect to this, the original one, and then I still get this thing here. So I still get here minus kappa times eta times wi, and this is also the up wi times t. Okay, so if I put these things together, what I get is that the new weight is the old weight at times t of 1 minus the kappa times the eta times, kappa times the eta, plus, or sorry, minus the kappa, the gradient, the original gradient that I had. So in my old algorithms, the weight would have changed, just the weight, the old weight, minus going a little bit in the direction of the gradient. If I have a regularization, what it means is that I take the new weight is the old weight, but slightly discounted. Okay, so this thing here is smaller than 1. Okay, so these parameters here are some small numbers that I have. And so this means these weights go a little bit down, plus I go a little bit in the opposite direction of the gradient. Okay, so this is generically, it has again nothing to do with neural nets, but this thing here, you see it sometimes, it's called weight decay. Okay, so it's another interpretation of what regularization kind of does. You're kind of at every step forgetting a little bit what the weight was. You shrink it a little bit, right? And then you just go then a little bit in the direction of the opposite gradient. Okay, so it's just an interpretation of this, what this could be. There's also another interpretation that it can also be useful. So this happens if you simply give it a regularization term here. You might also ask, and we did this already for the linear terms, you could also say, maybe you insist, okay, so you condition that the W, that this thing here is equal to a constant. So rather than saying I'll penalize models that have a large weight, and that because I add to this term W squared, maybe I insist that my model has to have a certain weight. Okay, the L2 norm has to be in a particular way. That's another thing that people often do. And so if you do this, then how could we proceed there? Turns out it's also not very difficult. So what happens is like this. So this is just a sphere, right? So in the beginning of the step, we are somewhere here, W of t, right? We're having somewhere a weight vector, and we're somewhere sitting here. And so now what we're doing is we're taking the gradient. We forget about this extra term here, and we're moving a little bit, right? So if we're moving, perhaps we're moving like here, okay? So perhaps we're moving to this step here. Right? So since when we take the gradient step, we don't worry about this constraint. A priori, we're going to be not on that sphere anymore, right? Clear? So what could we do now?
Project back.
Right? So this is just called the projected gradient thing. So we project back to be back on the sphere. And so we're simply looking for that vector that's closest to the vector here, again in this particular norm, right? The L2 norm. And that, is not hard to see that that's just going, shrinking or expanding. So we're just scaling things, okay? So in the L2 ball, that's quite easy. If you're looking for the vector that's closest, you just shrink or scale until you get exactly to have it the right norm. So that's very easy to do. So that basically costs us nothing. And that way we can always make sure, right? So we're here, maybe next time we're walking here, we shrink back. Maybe next time we're walking here, we shrink, or we scale up, etc. Right? So this is what's called projected gradient. Now this is nice if you do this with L2 norm, and that's often what you do with neural nets. If this projection is not always so nice, if you think about how to project on L1, then that's not just the scaling. Okay, it turns out to be more complicated, right? So L2 here is particularly easy. You just want to be on the ball. What's the closest point to the ball? You just scale. Very easy to do. Okay, then let's get to the last topic. Okay, the last topic is dropout. So, as I said, neural nets are not as prone to overfitting, and you can use regularization to overfit. But there's something that is very specific to neural nets, and that's what's called dropout. So this is something that is really, fairly specific to neural nets. Now, as with everything here, there's a billion versions of this dropout. So let me just tell you one random version, but there are many ways of how you can do it. So we have our neural net. And right now, we don't worry if it's convolutional or not convolutional and how many channels. We just think of our basic neural net that we have. Okay, so fully connected neural net with input x0, then layer x1, and then maybe at the end we're having the final layer here. Right, and what we are given is, again, as always, we have given some data, and this data is pairs xn and yn. And maybe we want to do some regression task, or maybe we want to do some classification task, and we already learned how we do the learning, right? We just typically do stochastic gradient, so we're having fixed, we start with our weights in some way, we have that fixed, we pick a sample randomly, we run the backpropagation algorithm, we get a gradient for that, we update a little bit, and we go on until hopefully we're happy, right? So now dropout is a way to, that has proven to be useful to get an even better generalization, so to get, to get less, these networks, so if you train them with or with dropout, they will be less prone to overfitting. And so the basic idea is the following. You don't actually train on that network here, but what you do is pick some probability p, okay, and maybe p is 0.9. Okay, you have some probability. And now what you do is, you flip, before you do any updates, like in the stochastic gradient, you flip, let's assume you do this for nodes, there's also versions you do it for edges, okay? You simply pick for each of these nodes, you flip a coin with that probability. And if, so p is 0.9, so let's say with probability p keep, with probability 1 minus p delete. So what we do is the following. If that turns out, if I flip a coin here, and I flip them independent for each of them, then there's a certain probability, let's say 10%, that I will actually delete that node, okay? It will come up, so it will be 1 minus p event. And then what I do is I simply delete that node from that network, okay? So what I will get is, after I've done this, I will get a sub-network. Is that clear? Right, so this results, this gives me a subnetwork. Right, and so in expectation, 90% of the nodes in this example, because p is 0.9, will survive, and 10% will be eliminated, right? But maybe you do it with p is a half. Half of them will be eliminated. And now what you do is, you remember all these weights you have, but then you simply look at the subnetwork and run a step in the gradient descent for that subnetwork. Clear? Then you get a new sample, you get a new subnetwork. Okay? So you do this many, many times, but every time you do it with respect to a different subnetwork. Now, if you do it like this, so let's assume your train looks crazy, how would you, why would you confuse the network? And now you're only allowed to do this and that and so on, okay? So how would you do in predictions? So let's assume this gives us anything meaningful. And now how would you do the predictions? Well, at the end of the prediction, there's several things you could do. Either, again, you ask maybe for several predictions, every time just, again, throwing independently 10% away and then getting several predictions averaging. That's one way. Clear? The other thing is you can do is, and that people do is the following. You keep the whole network for the prediction. But what you do is you need to kind of compensate for the fact that when you trained it, there were only 90% of these things in there, but when you predict that there's everything in there. And so one way you can do it, you can simply rescale all the outputs by that. Is that clear? You want to keep that at least in expectation, the whole sums and so on that you have there don't change. Make sense? Right? So it means, for example, one way is you keep the whole network, but you take all these things that you have, the outputs here, and you rescale them by this 0.9 here. Right? So then in expectation, the input that you get at the next layer in expectation of all choices of what things you removed is the same. Make sense? Yes?
Is the probability for each layer itself standalone or for the whole network?
No, for every, or if it's the same, or if it's, if
for every layer will take 90% of the nodes?
So you can do this, yeah, you know, you can do this for every layer different. You can do this either for the nodes or for the edges. Okay, so, I mean, again, billions of versions of this thing. Okay, simplest one is one probability, and you typically have a different probability of eliminating the original nodes, because these are inputs, these are kind of more important. You don't want to, you know, typically you don't throw away a lot of the input nodes, because, you know, that really throws in information, and often you have a larger probability here throwing things away inside. Okay, but again, it's just a parameter that you would use then for training. So, you know, why could that potentially help or not? Essentially what you do, one can show that if you use very specific activation functions, so this is not true for generic activation functions, but in some very specific settings, you can show that what you actually train here, what you're actually doing is that this corresponds to the average. So meaning this is kind of the same as if you had taken, so, you know, you're not going to get one network here, right? You're going to get a whole ensemble of networks here, right? Because for every node, you can either eliminate it or not eliminate it. So this means, you know, if you have, let's say, 10 nodes, then for each node, you can eliminate it or not eliminate it. A priori, you're going to get 2 to the 10 different networks, right? Is that clear? Right? And each of these networks will have a different probability of being there, because eliminating, you know, because you have just a binomial, right? To eliminate, if you have probability P to eliminate, and you have, let's say, in total n nodes, then to eliminate K and not eliminate some specific other ones, right, will be this, and if you just sum over everything, you get something like that, right? That will be probability that you get, that K of them will survive. If you're looking at the specific networks where you eliminate a specific K, that's the probability, right, that this survives. So you should think of not having one network, but having, you know, lots and lots of networks, right? So if we had n nodes, there would be 2 to the n possible networks. And since a neural net can have 1,000 or 1,000,000 nodes, you know, in your mind, that should explode, because there are 2 to the 1,000,000 possible networks that are behind this one network, right? Each of them with different probability. And so what one can show is that under certain, you know, conditions with particular activation functions, what this does is essentially train in parallel all these networks here, right? So it's as if you had written down each network separately, subnetworks. They all have slightly different structure, because there will be some nodes missing here, some nodes missing there, etc. You had trained all of them, okay? And then for each of them, then you would get a prediction. And the prediction that you get out of the whole network is kind of like the average of all these predictions. Clear? Now, these networks is, of course, not the same as if you had trained that number of completely independent networks, because these networks are all derived from the same network by just eliminating certain things. So they are not completely independent. But in general, model averaging is something good, right? So if you have, typically if you have 100 experts and they all are, you know, have some probability of being correct and they're independent, it's better if you actually pool their opinions, right? And so that's the same kind of idea, that you're asking like a huge number of networks what it is. You kind of, because of this special structure, you can train them all at the same time by doing that. And at the end, what you get as an output is the average of all these outputs. And that output, you know, is kind of intuitive in hindsight that this might be better than if you just took the output of one network. Make sense? Yes?
Under what conditions do you have this average?
So you need a very specific activation functions. Okay, I forgot. It's something like the sigmoid, but you need something very specific about that. Okay, and it's not exactly the average. It's close to the average. Okay, so there's a lot of almost in there, but that's the intuition. I mean, I think when Hinton came up with, I think they just tried it and it worked very well. And then people have tried to, explain why it works, and that's kind of averaging idea is one of the explanations. Okay, but this works also well when this activation function is not that activation function, in which case you cannot interpret it as an average, it's just kind of a, you know, an idea in the background why this might be a good idea. Okay, good. So we still have a few lectures. So remaining will be, maybe we still have a guest lecture, I don't know, but the rest will do some graphical models. And so we'll start on this Thursday to talk about graphical models. Okay?